Today I'll be dealing with the medicinal chemistry of alpha and beta blockers and central alpha agonists. I'm expecting you to be able to understand the mechanism of action of these drugs, and specifically I want you to be able to, when given a chemical structure, be able to recognize the chemical structures of alpha and beta blockers, um, knowing the pharmacophores. And the pharmacophore is the uh, part of the molecule that is the same across the family, same across the family. I should say the class of drugs. All right. So, what are the chemical structures that are the same, that are repetitive, of alpha and beta blockers? And also understand the role of specific functional groups as it relates to the pharmacokinetic and pharmacodynamic activities. Predict how key positions on the pharmacophore can influence the activity of the molecule. All right. So, quick overview here. Adrenergic drugs are employed in various different, in the treatment of various disorders, and the key is they can either be agonists or antagonists. There are adrenergic receptors all over the body, and we are going to look at some of the specific receptors and what therapeutic targets they can be used for. The foundation of these types of drugs is epinephrine and norepinephrine. Epinephrine and norepinephrine. Now, epinephrine is an endogenous neurotransmitter. Both epinephrine and norepinephrine are endogenous neurotransmitters. They are both known as catecholamines, type of drugs. So the catecholamines have an aryl ring, and then they have hydroxyl groups cis to each other. Okay, so this is a catecholamine structure right here. Okay, so they contain a dihydroxy, see hydroxy here, dihydroxy benzene ring. In addition to that, they also have the amine. Okay, now epinephrine and norepinephrine have an additional hydroxyl group at this position. Now, when you have a hydrogen, when R is equal to hydrogen, it's norepinephrine. When R is equal to CH3, is epinephrine. Okay, so these types of neurotransmitters are involved in the fight and flight response. So fight and flight response, you will have an increase in heart rate, increase in blood pressure, and you're shifting blood from every other part of the body to the skeletal muscles, so you can run or fight. And then you have a series of mechanisms that are going to lead to an increase in blood glucose. So you're going to have gluconeogenesis and glycogenolysis. So you're going to increase the synthesis of glucose, and you're also going to break down glycogen to release more glucose. So that's the fight and flight response. This is what happens when epinephrine and norepinephrine bind to the targets. Now, there are many different adrenergic receptors across the body, okay? And I want you to pay close attention to these adrenergic receptors, especially to those that can directly be targeted for hypertension therapeutics. So you have the alpha receptors in the arterioles and the vascular beds that can, when targeted by the epinephrine and norepinephrine, can cause constriction. Skeletal muscles, you have the beta-2 receptors that can cause dilation. Alpha-1 receptors, when epinephrine and norepinephrine bind to these receptors. You have contraction. In the heart, you have the beta 1 receptors, okay, beta 1 receptors that increase the heart rate and the force of contraction, okay. Then you look at the lungs here. You don't want to target beta 2, okay. You don't want to target beta 2 because they actually cause relaxation and bronchodilation, and you need that to breathe. Okay, so the ones that I want you to focus on, and I'm going to emphasize that in the next slide, are the ones that actually will help us in hypertension, targeting hypertension and therapeutics for high blood pressure. Now, okay, so again here, if you have an agonist at the alpha 1 receptor, these agonists can be used to treat shock, hypotension, and actually raise blood pressure. Okay. If you have an antagonist that binds to the alpha 1 receptor, this can be used as an antihypertensive. Okay, so I want you to remember that alpha 1 antagonists, can be used as antihypertensive. Okay, alpha 2 agonists can be used as antihypertensive. Beta 1 antagonists can also be used as antihypertensive. Okay, so alpha 1 antagonists, alpha 2 agonists, beta 1 antagonists, all right, and let me just repeat that again in case I made a mistake earlier. Alpha 1 antagonists, alpha 2 agonists, beta 1 antagonists. These receptors, alpha 1, alpha 2, and beta 1, when targeted by the right compound, can have antihypertensive use. Okay, so if you have an antagonist of the alpha 1 receptor, an antagonist that binds to the alpha 1 receptor, you can reduce blood pressure. Hypertensive treatment. Okay, make sure you remember this for your exam. Okay, all right, so let me keep going here. Now, when you talk about alpha and beta blockers, those drugs are going to be working mainly in the periphery. Going to be working mainly in the periphery, okay? Whereas alpha agonists are going to be working more centrally. We're going to go through all these different drugs in just a little bit here. Now, let's spend some time talking about the synthesis of norepinephrine, because it's actually very important for you to understand the enzymes that are responsible for the synthesis of norepinephrine inside of the body. Some of these enzymes will also be responsible for transforming, metabolizing drugs that have similar structures. Okay, now let's look at these images here. The synthesis of norepinephrine inside of the body begins with L-tyrosine, the amino acid L-tyrosine. And when you pay attention to the names of the enzymes, pay attention to the name of the enzymes, they actually clearly describe the role that they actually play in the synthesis of norepinephrine. For instance, tyrosine hydroxylase is going to convert L-tyrosine to L-dopa, and it does this by adding a hydroxyl group at this position here. Then you have aromatic L-amino acid decarboxylase, which is going to remove the carboxylic acid here, so decarboxylase, to give you dopamine. Okay, and then dopamine is going to be converted to norepinephrine by the enzyme dopamine beta hydroxylase. So you have a hydroxyl group that's going to be added at this key position here in the beta position of dopamine to give norepinephrine. Now, once norepinephrine is synthesized, it's going to be stored within the storage vesicles. It's going to be stored within the storage vesicles. So everything that I just talked about, beginning with tyrosine, okay, and you remember tyrosine is converted to L-dopa by tyrosine hydroxylase, okay, tyrosine hydroxylase, and then L-dopa is going to be converted to dopamine by aromatic L-amino acid decarboxylase, and then dopamine will be converted to norepinephrine by dopamine beta hydroxylase. So it's the same process that is drawn here. Once norepinephrine has been synthesized, it's going to be stored inside of storage vesicles. Okay, stored inside of storage vesicles. Now, all right. So it's stored inside of the storage vesicles. Now, there's a few things that happen. There's a few things that happen when norepinephrine is released. So norepinephrine is released from the adrenergic neuron. Released from the adrenergic neuron is going to go and bind to the effector cell. When it binds to the effector cell, it initiates a cascade of reaction that we've already seen earlier in the chapter, that are going to lead to increase in blood pressure, moving of blood from other areas of the body to the skeletal muscles, and initiate the fight or flight response. Fight or flight response. Okay. Now, some of the norepinephrine that's being released binds to the receptor and to the effector cell and cause that effect. Some of the norepinephrine is going to bind to the alpha-2 receptor on the adrenergic neuron in order to send a signal to the cell to stop releasing more norepinephrine. Okay. The extra norepinephrine is either going to be taken back by the cell through the uptake 1 mechanism, or is going to be metabolized by some enzymes that we're going to take a look at right here. The enzymes that are involved in the metabolism or the breakdown of norepinephrine in the body are monoamine oxidase, monoamine oxidase, okay, aldehyde reductase, aldehyde dehydrogenase, and then catechol O methyl transferase. All right, so here are these enzymes here, and again, the name of the enzyme tells you what the enzyme does. So the monoamine oxidase, so we look at these enzymes here. Let me pick one of the reaction that it does. For instance, this right here, catalyzed by monoamine oxidase. Yeah, you start by, so you basically convert this amine here to a aldehyde. Okay, now it's an oxidation because when you look at the oxidational state of this carbon here, you're gonna have, you go from a carbon that is gonna be bound to the amine like this with 2 hydrogens, and in this case you actually have a carbon that's bound to oxygen, another carbon and an oxygen here. So this particular carbon here has actually undergone oxidation. Okay, so monoamine oxidase. When you look at catechol O methyl transferase, Catechol or methyl transferase. This is a catechol ring, and there is a methyl group that's being transferred at this position here. Okay, and so on and so forth. You look at aldehyde dehydrogenase, you actually go from an aldehyde here to a carboxylic acid. So these are the enzymes that are involved in the metabolism of norepinephrine in the body. Okay. Now, before we get into some of the important drugs, I wanted to briefly mention some of the adrenergic blocking agents and the adrenergic neuron blocking agents. So these particular agents, their role is to affect the storage and release of norepinephrine. Okay, they affect the storage and release of norepinephrine. Originally, the drug reserpine is derived from an indole alkaloid from the roots of Raufolvia serpentia. It's a plant used in India to treat snake bites as a sedative. Okay, so what reserpine does is it replaces and depletes norepinephrine by inhibiting the active transport of magnesium ATPase that's responsible for storing norepinephrine and dopamine into storage vesicles. So let me quickly go back to this slide here. So what reserpine is going to do is going to block the mechanism that causes norepinephrine to be put into vesicles. Okay, so it's going to block that mechanism. So by blocking the mechanism, it's preventing norepinephrine from getting into the vesicle and going to lead to a depletion of norepinephrine here. Okay, so that's the role of that particular drug. Just want you to know what the structure looks like. Again, it's derived from a natural product. It's an indole alkaloid, and I don't have any questions on the exam specifically for reserpine, but I'm including it here for the sake of completion, and I want you to know what the structure looks like. Okay, all right. So moving on here, the alpha-adrenergic agonists. Alpha-adrenergic agonists. The big picture with this is that we have three different drugs. We have clonidine, we have Tenex, and Witensin. Okay, and I'm going to go through each one of those. So the generic names are guanabens and guafensin. So beginning with clonidine. Clonidine, it was originally designed to be similar to nasal decongestants. So the goal was to synthesize an alpha-1 adrenergic agonist that was going to cause vasoconstriction. But in clinical trial, it was observed that clonidine actually caused hypotensive effect. So more studies was done to understand the mechanism of action of clonidine. So I want you to think about clonidine as a drug that acts both on the periphery and centrally. Okay. All right. So in the periphery, it binds to the alpha-1 receptor as an agonist. And there it increases blood pressure through vasoconstriction. Okay. When it crosses the blood-brain barrier, though, inside of the brain, it's going to actually bind to alpha-2A receptors. Okay. Also binds as an agonist. When it binds there as an agonist, it actually causes a decrease in blood pressure through vasodilation. Okay. I also need to mention that still in the periphery, it also binds to alpha 2B receptors. Alpha 2B receptors. Okay. All right. And causes an increase in blood pressure. So when you look at clonidine, really you have two effects. So let's say you have a balance here, okay? You have a scale. On one hand, you have increase of blood pressure through the action at the periphery. On the other hand, you have a decrease of blood pressure through the action in the central nervous system, in the brain, okay, as we see here. But overall, the central reduction of blood pressure is more significant and longer lasting than the transient temporary increase in blood pressure. I hope this makes sense here. Now, when you look at the structure of clonidine, clonidine actually exists in equilibrium as a tautomer. Okay, and the imidazole ring is actually part of a guanidino group. And I want you guys to remember this. This is what we call a guanidino group here. Okay, we have these. You have these NH carbon. You have N. I'll put an R group here. Then another NH and R group here. Okay, so remember those structures and be able to pick it out. If I give you a series of drugs, be able to identify the guanidino group here. All right. So let's keep going here. So clonidine has that guanidino group, and the imidazole ring is part of the guanidino group. Now, when you look at the structure of clonidine, obviously you have this aryl group here, this aromatic group here, and then you have the two chlorines here. Now, because of the steric interaction caused by the two chlorines, the guanidino, the imidazole ring that is part of the guanidino group, and the benzene ring are actually not in the same plane because of the steric hindrance that's caused by these chlorines here. The benzene ring and the imidazole ring are not in the same plane. And let me also mention that the imidazole ring is actually not necessary for activity. Okay, you will see in the different analogs that we have, you still have a guanidino group, but it's not in a ring form. It's not in a ring form. So, as I was mentioning earlier, after studies of central alpha 2A agonists, it was found that the imidazole in the ring is not necessary for activity. Not necessary for activity. However, the phenyl ring and at least one chloro was necessary for activity. So open ring analogs were developed. Open ring analogs of clonidine were developed. These open ring analogs actually have the same mechanism of action as clonidine. Okay, same mechanism of action. So everything we've discussed earlier about clonidine, those drugs also do. Okay. Quickly here, methyl-dopa. Methyl-dopa is also an alpha-2 agonist, and it also affects, reduces blood pressure through central effect in the brain. It's actually a prodrug. It's actually a prodrug that's going to be metabolized to alpha-methylnorepinephrine. Alpha-methylnorepinephrine. Again, remember I talked to you about some of these enzymes that are going to come back. You have aromatic amino acid decarboxylase here. That's going to remove the carboxylic acid. Okay. Then you have dopamine beta hydroxylase. That's going to install a hydroxyl group at this position here. So methyldopa is actually going to cross the blood-brain barrier, and once it crosses the blood-brain barrier, gets inside of the CNN, that's where it's going to be converted sequentially by these enzymes to the actual active alpha methyl norepinephrine. Okay, and you have alpha methyl norepinephrine. So it's a norepinephrine molecule that has a methyl group here. Now this alpha methyl norepinephrine is going to selectively bind to the alpha 2A receptors, causing vasodilation. All right, so now let's talk about the alpha adrenergic receptor blockers. The alpha 1 adrenergic receptor blockers have been used for the treatment of hypertension. Okay, and in this figure we have the pharmacophore of these alpha 1 adrenergic blockers. Pharmacophore of these alpha 1 adrenergic blockers. So these drugs work because they are competitive inhibitors of norepinephrine for the alpha 1 adrenergic receptor. So selectively, they compete with norepinephrine for the binding of the alpha 1 receptor. Okay, and these receptors are located in the vascular smooth muscles. So remember, when norepinephrine binds to these receptors in the vascular smooth muscle, it causes vasoconstriction. So if norepinephrine binds, it causes vasoconstriction that then is going to increase blood pressure. Okay, so let's suppose this is the receptor and this is norepinephrine. Okay, when norepinephrine binds to it, causes a cascade of reaction that's going to lead to vasoconstriction and increase of blood pressure. So what these molecules are going to do, let me redraw this receptor here. Okay, what these molecules are going to do, you have norepinephrine in the system. Okay, but you're also going to have cardura. I'm just going to call it C. You have cardura. You have terazosin, and then you have minipress or prazosin. What they are going to do is they're going to bind to this receptor. Okay, let's say cardura binds to it, blocking norepinephrine from binding to the receptor. And when they do that, then they prevent the increase in vasoconstriction and the increase in blood pressure. Okay, and this is the alpha 1 receptor. So that's how these particular drugs work. Okay, now these drugs have a quinazoline. They are quinazoline derivatives, and they have a dimethoxyquinazoline ring that's attached to a piperazine. And again, when you hear these fancy names, look for what you know. Look for what you know. Dimethoxy. Okay, this is a methoxy group. This is a methoxy group. Okay, dimethoxyquinazoline ring. Okay, attached to a piperazine. Okay, so look for what you know, and remember those names. Alpha 1 adrenergic selective blockers used for treatment of hypertension have a dimethoxyquinazoline ring. Okay, dimethoxyquinazoline ring attached to a piperazine ring. So remember that. It's important for you to know these. Now, if you reduce the furan ring of prazosin to a tetrahydrofuran ring. Okay, so when you go from prazosin to terazosin, it leads to an increase in the duration of action by making the drug more resistant to metabolism. So let's quickly take a look at that, okay? So we're talking about going from prazosin to terazosin. We're going from prazosin here, to terazosin, okay? So what's the difference? What's the difference? One of the drug is a furan. Prazosin is a furan. Okay. Terazosin has a tetrahydrofuran, which basically means that you've added one hydrogen, two hydrogen, three hydrogen, four hydrogens here. You have removed the saturation and went from a furan to a tetrahydrofuran. And when you do that, you actually increase the duration of action. And I have some notes here on the metabolism of these alpha-1 receptor blockers for you. Okay, I have some notes there. I don't go into much detail about the metabolism in the lecture, nor do I go into detail on the exam. So let's spend the rest of the time here on these beta-adrenergic receptor blockers. Quick overview of these drugs. So the beta-adrenergic receptor blockers, they are going to block the binding of epinephrine and norepinephrine to the beta-adrenergic receptors. So some of these drugs are very selective for the beta receptors. Others also bind to alpha receptors. And we are going to look at how different classes actually have different selectivity. Okay. Now, beginning with the first generations, propranolol, nadolol, benbutalol, and pindolol, those first generations are actually, they bind both to beta 1 and beta 2. Okay, they bind both to beta 1 and beta 2 adrenergic receptor. They are non-selective. So first generation bind both to beta 1 and beta 2. Okay. Now the second generation actually specifically bind to the beta 1 receptor. So drugs such as metoprolol, for instance, metoprolol binds specifically to the beta 1 receptor, beta 1 blocker. Okay. And then the third generation have both alpha 1 and beta 1 adrenergic blocking activity. Third generation have both alpha 1 and beta 1 adrenergic blocking activity. Okay, so the majority of these drugs have what we call the aryl oxypropanolamine. Aryl, so you have some type of an aryl ring. Okay, you have oxy, propanol, so one carbon, 2, 3, propanol, and then you're going to have an amine. Okay, some type of an amine here. And when you look at the structures that are listed here, this is what you see. You have an aryl, oxy, propanol, amine. Okay, aryl, oxy, propanol, amine. I need you to be able to recognize that on an exam. Okay, now the S configuration of the carbonyl carbon is necessary for activity. S configuration is necessary for activity. So the carbon that we're talking about here is the carbon that has this hydroxy group here. So the S configuration is necessary for activity. All right. Let's keep moving forward here. Obviously, the most common aryl group is the phenyl group. There's a phenyl group. And on that phenyl group, substitution at the alto group of the phenyl with the small group is allowed. Okay, so you have substitution at the alto position, and that's allowed. When you have an indole group that replaces the phenyl group, you have intrinsic sympathomimetic activity. So let's look at one example, for instance. Pindolol. See, inside of the name, pindolol. See if I can change the color here. You have indole. Okay, so when you have an indole ring that replaces the phenyl ring, then you have intrinsic sympathomimetic activity. Okay. Obviously, the bigger when you start adding more lipophilic groups, more lipophilic substituents, you increase the lipophilicity of the drug. Okay. The hydroxyl group of the propanol, I should say, hydroxyl group of the propanol. Obviously, propranolol only has one hydroxyl group, but the hydroxyl group of the propanol is essential for activity because it forms a high affinity hydrogen bond with the asparagine. Okay, asparagine. So that hydroxyl group is important because it's going to form a high affinity hydrogen bond interaction with the asparagine inside of the beta adrenergic receptor. And that's the part where you need to know your amino acids. You need to know your amino acids, you need to know what they look like. I'm going to draw the asparagine structure here for you, and I will expect you to be able to draw it on the exam, okay? So let's begin by drawing. Okay. That's asparagine. That's the amino acid inside of the binding pocket that actually interacts with the hydroxyl group of propranolol. Okay, so it's very important for you to know these amino acids and to be able to recognize them on an exam. Phenyl ring substitution, monosubstituted auto-para substitution of the phenyl ring is going to provide beta-1 selective antagonism. So beta-1 selective antagonism is going to be facilitated by auto-para substitution of the phenyl ring, okay? And any other type of substitution pattern is going to lead to non-selective antagonism. So again, when you have auto-para substitution of the phenyl ring, is going to lead to beta-1 selective antagonism. So let's kind of scroll back quickly here. Scroll back quickly. Again, remember how we mentioned that second generation beta blockers are more selective for beta-1 blockers, for beta-1 receptor. It's because they have that auto substitution. They have auto substitution. They also have the auto para substitution. Okay, but for the most part, they have that auto substitution, and that auto substitution is what allows them to be more beta-1 selective. Okay, now all of the different substitution patterns, all of the different structure activity relationship patterns that we mentioned are actually listed on this figure here, and I'm going to briefly recap what we said. Okay, we're going to recap what we said. So we mentioned that you can have other aromatic systems here, particularly when you have an indole, you have higher sympathomimetic activity. Okay. Let me change this color here. Actually, let me erase this and write with that. So you have other aromatic systems that are allowed, but when you have an indole, you have intrinsic sympathomimetic activity. Okay. The auto pattern of substitution is going to give you beta 1 selectivity. Beta 1 selectivity for auto para substitution. The hydroxyl group here is essential to form a high affinity bond with the beta receptor of asparagine. Okay, and also remember this carbon has to be the S configuration for this carbon. The bulkier the R1 group, the more beta directing. Remember, some of these compounds can both be alpha and beta. So the bulkier the substitution at the amine more beta selective they are. And substitution at the either substitution or the size of the aryl ring here is going to either increase lipophilicity or hydrophilicity of the drugs. Okay, we just mentioned lipophilicity. Those drugs are reported to have good bioavailability, and I have some facts here about the metabolism of the drugs that is here for your information, but we won't really go into a lot of details with those. All right, I want to mention quickly before we close this chapter here the mixed alpha and beta adrenergic receptor blockers, and these are the third generation. Okay, so they block both alpha receptors and beta receptors. When you look at those molecules, they have a chiral center, okay, and they are administered as a racemic mixture. S-carvedilol has alpha 1 and beta blocking activity, while the R isomer only has alpha 1 blocking activity. Now when it comes to labetalol, only the RR isomer is active. Yeah, let me say that again because this is important. When it comes to labetalol, only the RR isomer is active. Okay. All right, this concludes this lecture. I hope this helps for the exam.